If you take a metal wire and pull it taut, you are doing physical work. You are applying force to a material, and standard physics tells us that work transfers energy into that system. We expect that energy to show up as a measurable increase in temperature. The wire should get warmer. But when you actually measure it, the thermometer drops. The reading slips downward, settling lower than when the tension was first applied. You are forcing energy into the material, pulling harder and harder, yet the metal is actively getting colder. The heat didn't simply vanish due to a faulty measurement. That persistent cooling effect points directly to a gap in our understanding of what energy is doing inside a solid object. This anomaly caught the attention of William Thomson, later known as Lord Kelvin. He spent his career trying to define the physical mechanics of temperature. Picture a crowded room. People are shoulder to shoulder, constantly bumping into each other. On a subatomic level, that chaotic motion is heat. Now stretch the room. Give everyone more space. Collisions drop, chaotic movement settles, and the overall temperature goes down with it. Kelvin suspected a similar mechanism governed the atoms inside a metal wire. He set up a precise experiment in his lab, rigging a thin wire between two rigid supports and attaching a highly sensitive thermometer to wait for thermal equilibrium. He slowly added tension. As the wire elongated by a barely visible fraction, the temperature reading steadily ticked downward. Since the system was isolated and the results were highly repeatable, the mechanical energy he was adding had to be going somewhere. The wire was somehow absorbing the work without translating it into thermal vibration. The next step was to see what happens when you reverse the process and let the tension go. The temperature doesn't merely return to its starting point. It spikes, briefly making the wire significantly hotter than before the experiment even began. When pulled tight, physical work forces the atoms out of their disorganized state, locking them into ordered structural alignment. The moment tension is removed, that order collapses. The stored energy snaps back as chaotic vibration, creating a sudden heat spike. The solid metal is acting as a storage system, constantly shifting energy back and forth between two states, internal structural order and observable thermal motion. Kelvin decided to test the limits of this exchange by increasing the variables. He clamped down a much thicker wire and applied a massive amount of physical force, anticipating a severe temperature drop. The thermometer barely registered a change. Under high force, the cooling effect essentially vanished. The assumption that brute force guarantees internal rearrangement was incorrect. The deciding factor isn't the amount of force you apply, but the specific atomic flexibility of the material you are pulling. Some metals have flexible atomic bonds that easily slide into new, highly ordered arrangements, which triggers the cooling. Other metals possess extremely rigid bonds that refuse to reorganize, meaning the added energy stays trapped as vibration and the temperature remains stable. This split-screen chart illustrates the difference. On the left, tracking sheer physical force against temperature yields a flat, unpredictable line. On the right, tracking strain, the actual percentage of physical deformation, shows a perfectly clear, steep downward trend in temperature. The material's own internal resistance acts as the gatekeeper. It alone dictates whether the physical work you apply becomes sensible, measurable heat, or gets tucked away into hidden structural alignment. To map the boundaries of this effect, Kelvin continually increased the tension on a flexible wire, tracking the temperature as it steadily dropped lower and lower. As we see on this graph, the descending temperature line eventually bottoms out and plateaus horizontally. Even as more physical tension is applied, the cooling stops completely. At this plateau, the internal structure of the metal has reached its maximum possible state of atomic alignment. It is perfectly ordered and physically incapable of storing any additional structural energy. Once that structural capacity is completely maxed out, you are still adding physical work to the system. With nowhere left to hide in the material's geometry, that fresh energy is forced back into chaotic motion. Every physical system possesses a hard mathematical limit on how much energy it can store as internal structure before the excess inevitably spills over into observable heat. This leads to a counterintuitive conclusion about the physical world. Temperature isn't a direct measure of how much total energy a system contains. It simply tells you how that specific amount of energy is currently distributed. Today, this is known as the thermoelastic effect. It is the same underlying mechanical principle that explains why pressurized gases cool as they expand, and it forms the physical basis for modern solid-state cooling technologies. You can test a variation of this yourself. If you pull a heavy rubber band completely taut, hold it against your lip, and then suddenly let it go, you will feel a sharp spike in heat against your skin. A simple stretch of a wire reveals that energy is constantly moving through hidden pathways. It leaves a lingering question about our immediate surroundings. How many other everyday physical interactions are silently absorbing and transforming energy right in front of us, completely undetected?